Hi, I'm Ramin Mojab. In this video, I'm going to talk about the probability function, and this is the second session of a more general program on statistics and econometrics. Let me give a summary first. In the previous session, we talked about the sample space and the sigma algebra on the sample space. Here we will use them and we'll talk about measurable space, measure and measure space. We'll use these and we'll talk about probability space and probability function, and we'll talk about axioms of probability too. We'll have some examples and we'll define events with zero probability or almost sure events. Our discussion starts by introducing this concept: measure space. Let omega be a set and sigma be a sigma algebra on the set. This ordered pair in which the first element is a set and the second element is a sigma algebra on the set. This is a measurable space, and every member of sigma is a measurable set. If you recall from our discussion in the previous session, you should know that if omega is the sample space of an experiment, then every member of sigma is also an event. Here we say that if we define this ordered pair, or if we define this measurable space, then every event is also a measurable set. Now consider this ordered triple. The first one is a set, the second one is a sigma algebra, the second element is a sigma algebra on the set. Here we have a measure too. What is a measure? A measure is a set function. A set function, it means that it is a function that you give it a set and it gives back something, for example, a real number. A measure is a set function from a sigma algebra to the extended real numbers. Okay, this is the extended real numbers. It satisfies three properties. The measure of the empty set is 0, the measure of every set is not negative, and here the measure of if we have some disjoint sets, the measure of the union equals the summation of measures, or in other words, for all countable, this countable is related to these infinity signs here. For all countable collections of pairwise disjoint sets, this equality is satisfied. So these are the three properties of a measure. As an example, consider this ordered triple. Here the set is the set of natural numbers, which is a countable set. This is the sigma algebra on this set, and this is our measure, and we'll talk about it in this slide. Omega is a countable set, and therefore every member of sigma, or every measurable set, is also countable. For example, this is a measurable set and it is countable x such that x is even, or this is a measurable set and it is finite and countable. Here the measure of E, or n of E, counts the number of elements in E, in which E is a measurable set. It is known as the counting measure, and we will use it later to prove some propositions in the probability theory. Anyway, it has three properties. The number of elements in the empty set is 0. The number of elements in every measurable set is not negative for all E in sigma. And for this pairwise disjoint sets, the number of elements in the union equals the summation of the number of elements. As another example, consider this ordered triple. Here we have R, the set of real numbers. This is continuous. We have this sigma algebra, which is known as the Borel sigma algebra on R. You might write it B of R. And I will talk about it in the next session. This means that our measurable sets now are intervals or unions of intervals in which these intervals might be open, closed, or half open, or also our measurable sets might be sets of numbers such as the set of rational numbers or set of natural numbers. This measure here is known as the Lebesgue measure on R, and it calculates the length of A, the length of a measurable set. If A is an interval, then the Lebesgue measure of this interval is B minus A. You might be familiar with this length. If it's an open interval, nothing changes. Again, its length is B minus A. If it's a union of two intervals and they do not overlap, then the Lebesgue measure of this union equals the sum of the lengths. If they overlap, then the Lebesgue measure is less than the sum of the lengths. If A, or our measurable set, is a countable set, then its measure Lebesgue is 0. For example, the Lebesgue measure of rational numbers, the set of rational numbers, is 0. Lebesgue measure of the empty set is 0. This is related to the first property of a measure. We know that the Lebesgue measure is not negative. This is related to the second property. And here this one is related to the third property of a measure. Now we can talk about probability space and probability function. Consider this order triple, which is a measure space. Here omega is not just a set or the set of the measure space, it's a sample space in an experiment. And this order triple, which is a measure space, is also called a probability space, and P, which is a measure, is also called a probability function if and only if the measure of the sample space equals 1. Note that P is already a measure and therefore it satisfies 3 properties. Here we added another property and therefore it satisfies 4 properties known as the axioms of probability. I will use the terms that we introduced in the previous session. For example, here for the first axiom, I'm not going to say that the probability of the empty set is 0. Instead, I say the probability of the impossible event is 0. This is the first axiom. The second axiom is the probability of any event is not negative. The third axiom, the probability of the certain event is 1. And for a countable number of events, the probability of the union equals the sum of probabilities. Is there enough information to calculate this one here in the fourth axiom? The answer is yes. If you recall our discussion in the previous session, you should know that this set, this union, is a member of the sigma algebra due to the definition of the sigma algebra. Therefore, you can say that it's a measurable set and therefore we can measure it, or you can also say that it's in our information set and therefore we have enough information to calculate it. We can prove some propositions. Let this order triple to be a probability space and E and F be 2 events. We can show that the probability of an event plus the probability of its complement is 1. In order to show this, you need to use this axiom, the probability of certain event is 1, and this fact that the union of E and its complement equals a certain event, and this fact that the E and its complement are separate events, and also the fourth axiom. And then you can easily prove this one. For the second case, you should use the first one, which means that the probability of any event equals 1 minus a positive number. Note that from the second axiom, we know that this is not negative. The third one, you should use this fact that E minus F and the intersection of E and F, the union is E. Okay, and these are separate events, and therefore you can use the fourth axiom and easily prove this one. And for the fourth case, you should substitute P of E from this equation, and there is a similar equation for P of F, and you should substitute them and you can easily prove it. Here for the fifth case, you should define G such that an event such that the union of G and E equals F, and G and E are separate events. And therefore, you can use again the fourth axiom and easily prove it, that if E is a subset of F, then its probability is equal or less than the probability of F. Here we have a countable partition on omega, which means that these partitions, the union of these partitions equals omega, and they are pairwise disjoint sets, and the probability of any event equals the summation of this intersection. Again, it's easy to show this one because E is the union of these events. So here we have E, and also these events are separate events, and therefore you can use the fourth axiom and easily prove it. This is known as the law of total probability. As an example, consider disordered triple. Here omega is discrete, which means it's finite and countable. And we want to talk about this ratio in which n is a counting measure. And we want to, for example, say that the probability of E equals number of elements in E over number of elements in omega is a probability function. Note that we used it in the previous session and calculate a probability. Okay, it's easy to use the properties of n and prove that the axioms of probability are true here. For example, number of elements of the empty set is 0, therefore numerator is 0, and therefore the probability of the impossible event is 0. Or number of elements is not negative, or the counting measure is not negative, therefore the probability here is not negative. Or for example, we should use this property, number of elements in E1, if E1, E2 so are pairwise disjoint sets, then this equals the number of elements in E1 plus the number of elements in E2, and so on. We can use it and prove that the fourth axiom is also true here. Therefore, this is a valid probability function. I have an exercise for you. I want you to check that if the axioms of probability are true for this ratio. Note that omega is here finite and countable, and n is the counting measure. In the previous example, we talked about discrete sample spaces. Here we want to talk about infinite discrete sample spaces. For example, the sample space in an experiment in which a random natural number is obtained. We talked about this experiment in the previous session too. And in this slide, we want to show that we cannot use this as a probability function when we have an infinite discrete sample space. To show this, note that if the fourth axiom is true, then the probability of E1, the probability of this union equals the sum of these probabilities. Okay, E2 and so on. Now consider a case in which E1 is a set of just one element, or EI for all I is a set of just one element. WI is a is an elementary outcome, and these sets have different elementary outcomes because they are separate events. Okay, now we can say that the probability of E1 is 1 over n, or m, in which m is the number of elements in omega. The probability of E2 is 1 over m, and so on. As you can see, if we use this formula or this ratio and the fourth axiom is true, then the probabilities are equal. The probability of these events are equal. Now consider a case in which we have an infinite discrete sample space. The probabilities are equal, or the fourth axiom is valid or true, and the probabilities are equal and equal to epsilon, which is a positive number. And the probability of the sample space equals the probability of this union, I from 1 to infinity, EI is this set, or this event. This is sum of these probabilities, probability of EI, which is infinity, or epsilon plus epsilon, which is an infinity, positive infinity, and this is not equal to 1. In other words, if the fourth axiom is true, the second axiom is not true, and therefore this is not a probability function for this case. Now consider a case in which we have infinite discrete sample space. The fourth axiom is true, and the probabilities are equal, but the probabilities are 0. In this case, we can easily show that the probability of omega is 0, which again is not equal to 1. Therefore, again, in this case, if the fourth axiom is true, again the second axiom cannot be true, and therefore this function, or this ratio, is not a probability function for an infinite discrete sample space. For the infinite discrete sample space, consider this set, or this event, in which x, we select a random natural number, and this number is an even number. You might guess that the probability of this event must be 1/2. And however, we cannot use this ratio, the number of elements in E over the number of elements in omega, to show that, for example, this is 1/2. In order to show this, we need an asymptotic version of this formula. In this case, for example, define f set of natural numbers such that x is natural and x is equal or less than the number of elements n, and x is even. Okay, here and this function p of f equals limit of this ratio, the number of elements in the intersection between f and 1 to n, this function over n when n approaches infinity. It's easy to use this formula and show that this probability of E, the probability of this event, is 1/2. However, this formula, we should show that the axioms of probability are true for this formula. For example, p of the empty set is 0, or p of the omega is 1. Omega here is the number of the natural set is 1, and other axioms. I leave it unexplained. As another example, consider this order triple. Here the set is a continuous set, or we have a continuous sample space, and we want to talk about this ratio. This is the Borel sigma algebra, and I will talk about it in the next session. This ratio is a probability function. In the previous session we used it, and we calculated a probability. And mu here is the Lebesgue measure on R. And we can use its properties and prove that the axioms of probability are true for this ratio. For example, the mu of the empty set is 0, therefore the numerator is 0, therefore the p of empty set or p of impossible event is 0. Or mu of omega over mu of omega is 1, therefore the third axiom or p of sigma or the certain event is 1. Or mu is not a negative number, therefore this ratio is not negative. Or mu of E1, the union of E1, E2, and so on equals the length of E1 plus the length of E2 for pairwise disjoint sets, E1 and E2. And therefore we can easily use this and prove the fourth axiom too. Generally, this ratio is a probability function when we have a continuous sample space. Note that events or measurable sets might be more complicated than being just intervals when we are dealing with continuous sample spaces. For example, Q is in Borel sigma algebra, the set of rational numbers, and therefore one might ask, what is the probability of obtaining a rational number when we select a random real number? You can use one of the properties of the Lebesgue measure on R and say that since Q is a countable set, then its Lebesgue measure is 0. Therefore, if we use the previous ratio, the Lebesgue measure of Q over the Lebesgue measure of R, the numerator is 0, and therefore this ratio is 0. Therefore, the probability of this event is 0. Of course, you can explain it in another way. If you want this number or any other number, 4.2 or any other number, to be a rational number, you should have an infinite number of zeros here. This means that if you select a random integer between 0 and 9 for an infinite number of times, each time you should obtain 0. This is not impossible. This is not an impossible event, but its probability is 0. I will talk about it later. Therefore, the probability of obtaining a rational number in this experiment is also 0. As another example, consider this function, which is known as the characteristic function or the indicator function. This is a set function. For a given w, w is in omega. If w is in e, then the value of function is 1. Otherwise, the value of the function is 0. For a given w, we want to use this function and construct this probability function in which for a given w, p of e is delta of e. It's easy to show that this is a probability function, or the axioms of probability is true here. For example, delta of the empty set is 0 because for all w, w is not in the empty set. Or delta of omega is 1 because w is in omega for all w, and we are here in this part of the function. Or the value of the function is 0 and 1. These are non-negative, and therefore another axiom is also true. For the last axiom, consider these separate events. We have two cases. The first one, w is not in any of these events, and therefore w is not in the union of these events, and therefore delta of this union is 0. And also the summation of this summation, delta of E1 plus delta of E2 and so on, this is also 0 because these are 0. 0 equals 0, and therefore the last axiom is true here. On the other hand, if w is in E1 and w is not in any other event, E2 and so on, Here W is in the union of these events, and therefore delta of this union is 1. And it's easy to see that this summation, delta of E1 plus delta of E2, so on, this is 1, 2, because this is 1 and this is 0 and the others are 0. And therefore 1 equals 1, and the last axiom is true here. And we do not have any other cases because these are separate events. I am going to define zero probability events in the next slide. Before that, you should get familiar with this concept, null set. Let this triple be a measure space. A measurable set such as E is a null set in this measure space if and only if its measure is 0. Null set, or you can say a set of measure 0. For example, the empty set is a null set in every measure space, or every countable subset of R is a null set in this measure space. Note that, for example, Q, or the set of all natural numbers, are members of this Borel sigma algebra. And we talked about it, that the Lebesgue measure of, for example, Q is 0. However, some uncountable subsets of R are also null, for example, Cantor set. Of course, I'm not going to introduce this concept or talk about it. Just note that these sets exist. As the name suggests, zero probability event is an event with zero probability, or in other words, E is a zero probability event if and only if the probability of E is 0. An impossible event is a zero probability event. You know that P of the empty set, or the impossible event, is 0. On the other hand, if a zero probability event is not the impossible event, then it might occur. For example, consider an experiment in which a random real number is selected, and we know that D is obtained. A real number is obtained. Now, we define this event, E, which is an interval, and let omega be this interval, which means that the length of omega is 1. Therefore, the probability of our event here is b minus a over 1, the length of omega, which is b minus a. On the other hand, the length of this interval, d and d, this interval, mu of this interval is 0, and therefore the probability of obtaining d for all d in R is 0. However, here we said that D is obtained. Yet D is obtained. Is this a contradiction? The answer is no. It's a zero probability event that might occur. We have an almost sure event too. An event is an almost sure event if and only if its complement is a zero probability event. For example, omega is an almost sure event because we know that its complement is the empty set and its probability is 0. And if an almost sure event is not omega, then it might not occur. We also have an almost surely true statement, or we say that a statement is almost surely true, or a statement is true with probability 1. If f of w is a statement, then f of w is almost surely true if and only if this event, which says that f of w is true, is an almost sure event. For example, I'm going to use the previous example. Let d be a real number, and we have an experiment in which we obtain a random real number. This event, E of d and d, this was we show that this is a zero probability event. Its complement is an almost sure event. Or one might say that we will not observe D for all D in omega. This is almost surely true. Or one might say that we will not observe D for all D in omega with probability 1. Get familiar with this term too. Almost everywhere means a statement such as f of w is true everywhere except on a null set. For example, you are familiar with this function. This is the characteristic function that we discussed before. If E is the set of rational numbers, then this is known as the Dirichlet's function. And we say that Dirichlet's function is equal to 0 almost everywhere. I mean this part of the function. And this is because we know that the Lebesgue measure of Q is 0. Thanks for your time. I will talk about random variables in the next session. Also note that I'm still learning statistics and any comment is appreciated.